Hi, everyone. My name is Min. Thank you for joining today's ELISA online virtual seminar on AvioNix, Infrastructure as Code for Linux in Avionics. Today, we're very delighted to have two speakers for this seminar. Please welcome Wanja Zaeske, who is a research scientist at German Aerospace Center, and Erin Vanderveen, sorry about the pronunciation. Erin is a senior specialist functional engineer at Tweag by Modus Create. Without further ado, I would like to pass the microphone to Wanja and Erin.
Okay, well, pronunciation was perfectly fine. Thank you for the nice introduction. I'm going to start off this presentation or this seminar by talking about Nix, and then Wanja will take over and talk about specifically avionics and Nix and avionics. I'm here because I love talking about Nix, and I love to introduce new people to Nix. So I'm really excited to get going. So I want to welcome you to a deep dive into Nix. I'm going to talk about low-level concepts, and then we're slowly going to build up to a bit higher level concepts and the advantages of Nix. I want everybody to follow along. So at the end of every slide, I'm going to have a short moment for questions, just 10 seconds or so. So if you have a question, please ask me then and there, so we don't have to wait to the end to make sure everybody's following. And I love talking about Nix, so giving me excuses to talk more about Nix are very welcome. Cool. All right. So first thing we need to talk about is that Nix is not really a single thing. It's an idea, a philosophy, an ecosystem. And so when we talk about Nix, we're talking about one of many, many different things, or the thing as a whole. So before we can get into the actual weeds, we need to understand what we're talking about when we're talking about Nix. I'm going to quickly go through this list. First, there's the Nix CLI. This is the tool that you'll use when you're in your terminal and you want to build software, or you want to enter a dev shell, or you want to build an operating system, or anything of the sort. This is what you'll type into. It's sometimes called Nix CPP because it's written in C++. The Nix CLI talks to the Nix daemon, which is running on your system as a root or under root, and those two communicate with each other. So when you want to build a package in the CLI, it will talk to the Nix daemon. The Nix daemon will actually do the building, and the Nix daemon also manages the Nix store. The Nix store is a database of individual packages that ultimately everything you do on your system, so entering a dev shell or building a package, will end up somewhere in the dev or in the Nix store. There's going to be examples later, so no worries. To get stuff into the Nix store, to build a package, you need to write something in the Nix language, which is sometimes called a Nix expression. It's just a functional declarative language. We're going to see examples in my presentation, but way more examples in Wanja's part of the presentation later. And then there is Nix packages, which is a collection of Nix expressions that are made by the community for the community. There's 160,000 or more than 160,000 expressions when I last checked, which was last week. And that makes it the largest repository of software packages, libraries, everything in the world, which is one of the things that makes Nix so incredibly powerful, is how easy it is to add new packages to Nix packages. And finally, there's NixOS. I'm not going to go very depth into NixOS, but it takes the idea of being able to build a package and applies it to the entire operating system. If you can build a package, you can build an operating system, and then you have full reproducibility of your entire operating system. Any questions? 10 seconds. Okay, cool. Then we're going to talk about key concepts. So the first one is the Nix store I mentioned earlier. What you see here on the slide is an actual snapshot of my Nix store as it was this morning. And as a recap, whenever you build a package or whenever you add a package to your environment, it ends up in the Nix store through the Nix daemon. So for instance, here, I don't know if you can see my cursor, but around halfway, there's GNU grep. So on my system, I have GNU grep explicitly declared as a package that I want to install. And so when I build my operating system, the Nix daemon adds it to this store, right? This GNU grep might refer to other packages that are also in the Nix store. So for instance, GNU grep doesn't depend on libtiff, but let's say it does. There will be a reference from this Nix store path into libtiff. It's important to know that the Nix store is just a directory on your hard drive, right? And all of these are either subdirectories or files. Then what you'll see up here are these DRV files. We're going to talk about those a little bit later. And what you'll also see is the source here. So when you build something with Nix, in order to ensure a reproducible build environment, it first copies the entire source of what you're trying to build into the Nix store. That's what this is. I don't know which package it is. It's not mentioned, but at some point I would have built something that ended up in the Nix store. And finally, because we have this NixOS system, my entire configuration is written in Nix and is also added to the Nix store. And then the Nix system at startup makes a symlink from my home directory at .config/fish, I think, into the Nix store. Okay. Now, all of these are identified by this hash in front of them. Right. The hash refers not to the content of the package, but to the entire build environment that the package was built in. So it contains all dependencies all the way up to Nix packages bootstrap, which is OpenSUSE, I think. And it includes the source of the package. It includes the individual build steps of the package. Everything that's in the environment. We have a question. Does the store always grow over time, or how versions are managed? This is a really cool question. So by default, the store grows and grows and grows. Say I have a version of GNU grep, and I've installed it into my environment, but then later Nix packages gets updated, and there's a new version of GCC that gets put in. Then of course this hash would change because GCC is an input, is part of the build environment of GNU grep. So then if I would update my system, a new directory would get added to the Nix store with this new version of GNU grep. But Nix can do garbage collection. So if you invoke the garbage collector, you can tell it how many generations of the package you want to keep. But it will by default look at all the packages that aren't needed in the current system as it is, and just remove those from the Nix store. The nice thing is that Nix is reproducible. So if at any point you do need those old packages again, you can just get them again. Any other questions? I'll give you another 10 seconds. All right. Next core call. Oh, no, sorry. This is what the Nix store path actually looks like. This is GNU Hello, which is the Hello World program made by GNU. And as you can see, it is FHS-like. The Nix system ensures that stuff gets added to your path, for instance, based on this FHS-like layout. What is a typical problem Nix claims to solve is one of the questions I got. we'll talk about that later. I want to talk about core concepts first, and then we're going to see how this all comes together to solve the big picture. This is an example of a Nix expression. I won't go into detail because Wanja is going to talk about, is going to show more Nix expressions later. But I am going to talk quickly about the individual components. So this make derivation we're going to see, but what will end up happening is that this piece of Nix code, this expression, gets turned into a derivation file. It's on the next slide. Hold on. And the derivation file lists all the dependencies that are necessary to build this file, and they are explicitly listed here. So you define the name of the package, the source, which can be a local source like here. It can also be an upstream source like a Git repository. That's all fine. And you explicitly define every build input. For instance, libyaml, because GNU hello reads from a YAML file. Package config, because we need to find the libyaml at build time. And then you define the imperative build steps to build GNU hello, right? So Nix ensures the environment is set and reproducible, and then the steps, the individual build steps, are still imperative. You might be asking, where's GCC? Where's make? Those are all encapsulated in std-env. std-env creates a standard environment that most C, like with software that most C programs would need to be built. So it contains things like copy, make directory, GCC or Clang, or CMake, make, the auto-config scripts, they're all in there. Then make derivation creates a file that looks like this. You don't have to read this, but understand that this is a JSON file that the Nix daemon gets from the Nix CLI and evaluates into an actual package that gets added to the Nix store. If you're very attentive at this point, you'll notice that the Nix language isn't actually necessary for the Nix daemon and the Nix store, so you can actually use different languages. It's a bit of a tangent, but GUIX does that. They use Lisp instead of Nix. Another question, are all the components you're talking about typically used together, or could you use Nix packages or build packages with Nix on different OS? You can absolutely use a different OS. Yes, NixOS actually came later. So first there was Nix and then it came NixOS. NixOS is a build system on its own, and you can extend that to build an operating system, but you don't need to. You can always just build the package or individual packages. Or what you can even do is only manage your home directory using Nix, but not the system. And Nix also runs on macOS and BSD and kind of on Windows. Somebody raised their hand. Is that true?
That was me, actually. I would like to point out, while it's perfectly possible to run just Nix without the other things, I saw most engineers that are, let's say, intoxicated with Nix eventually switch to NixOS in the end, because they can just use the same mechanisms to solve a wider scope of problems they face, in particular configuring the development machine that they work on. So definitely possible, but beware of any side effects that might conquer your will.
Nix is addictive, but you have to be a little bit of a sadist to use it, because standard software doesn't run on NixOS. So I always suggest people to start with Ubuntu, Debian, whichever, install Nix, see its benefits, because only then are you willing to accept the downsides. The downsides being not able to run a lot of software that you just download from the internet. All right, cool. So this was the earlier question. What can we solve with Nix? And this is what you'll find on the NixOS website. These three keywords: declarative, reproducible, reliable. Don't read them if you don't want to. But the core is that Nix creates a declaratively reproducible, reliable build system or build environment for you to build your packages or operating system or operating system image or whatever in. It's declarative in the sense that you describe the end result. It's reproducible because of the hashes, and it's reliable because everything gets moved into the NIC store and gets built without any access to any other part of your file system. So nothing can leak into the build process, nothing can leak out of the build process, and everything refers back to something in the NIC store. That means that dependency hell is solved. When you build a package with NICs, it only refers to things in the NIC store. That means that there's never this issue of I need to install a certain version of a package before I can build my own, or, oh no, I have two versions of the same package that I need to install at the same time. Because there's nothing written in the FHS. So the NICs never looks at standard locations for files, except for bin sh. And that's super powerful. It solves developer environments. This is a really cool history fact, but those came second. NICs was first just there to build packages, and then they realized, wait, if we have this reliable, reproducible environment to build packages in, why don't we just give that to the developers for them to develop their packages? So I have a short demo. I hope the video will work. Otherwise, I can have a backup plan. Let's see if the video works. So I'm going to describe what's going on. I have a cargo project here, just an example. And I'm trying to run it, but it doesn't work. So what I can do, oh no, what I can do is I can pull cargo from NICs packages into my current shell. Uh-oh, I still don't have GCC. So I can pull GCC as well. And then I can run my package. Yay. Now, this is not reproducible because NICs packages refers to the NICs packages that I currently have or that I've currently used for my system, right? So instead, what you can do is you create something called a flake.nix file, which the repository that Wanja will show later has one, I think. And what you can do then, instead of manually pulling them in, you can type nix develop. And you enter a bash shell that has cargo available, and it just builds. I can show you what flake.nix looks like. Here it is. This is all the build inputs that I've defined for my system. So one of those is also Clippy, which means that now that I'm in dev shell, I can also do cargo Clippy. Okay. Now this flake.nix refers to a specific commit of NICs packages. So everyone who enters this dev shell gets exactly the same build environment, assuming they're all on x86, 64 Linux. Right? If you're on ARM, you get a slightly different version, of course. NICs can't change your architecture of your CPU. Okay. Is there some namespacing or other feature for NICs packages to easily identify official versions of packages? NICs packages are a bit like the Arch user repository. So there aren't really official versions of packages. They're all contributed by either core maintainers or external contributors that make a PR that's then reviewed by a maintainer and gets merged into it. What you can do, I didn't plan on talking about this, but what you can do is some software maintainers will publish a flake.nix in their repository, and then you can refer to official packaged versions of their software. But that's rare. It's getting more and more common, but it's currently pretty rare. So I think the R has no maintainer review process. Oh, I'm sorry. Okay. I'll trust you, Wanja. I didn't know that. I'm not an Arch guy. But yes, it's pretty hard to get in to push something into NICs packages, and it's reliable. But there's no way to talk about official packages Because like even when you look at Debian, there are no official packages, right? The Debian maintainers package those packages. Oops. Then traceability. For clarity's sake, this is the derivation file that we looked earlier. I don't want to go into depth again, but note that it lists every exact dependency that we have, and that allows Nix to create SBOMs that are incredibly precise and detailed. And there are different tools for that. And in this one, I used the tool that was developed by Tweag, because that's where I work, makes sense, to create a Cyclone DX SBOM of, I think I do hello as well. Yes. And it's just an SBOM. One of the cool things is that because all the store paths are unique and uniquely defined by their build environment, we don't need to have special references, BOM references. We can just refer to the store path. I think that's cool. Thanks for SBOM. Yes, SBOM is software build materials. Thank you. I think I'm going to leave this slide because I don't think it's very important for to understand, but this is kind of what a NixOS system looks like, where you define the file system, you define all the packages that are available, and you can even define systemd services and things like that. But I'm going to skip this.
I think actually it makes sense to go into this to some detail. You earlier said this already, but I want to reiterate. A Linux distribution in the end is just a bunch of files and a mechanism to push these files to a machine upon user request. And so this entire mechanism that we call NixOS in the end is just a bunch of files, a couple shell scripts, and a couple of Nix expressions that describe how packages are built that together compose a distribution. The important thing to realize here is that a package not necessarily is I download some C program and I compile that and then I have an L file in the end. A package could also be that I write a text-based configuration file that, for example, contains my pluggable authentication module configurations for the PAM stack in Linux. So yeah, maybe we can change to the other screen share.
Oh, yeah, let me stop.
With a bit of luck, you should be able to see my screen now.
Not yet.
Does it work?
There it is. Yes.
Perfect. So thanks, Erin, for the introduction. I've tried to explain or make this introduction myself a couple of times, and it's always hard. So I think you did a good job here. Thank you for that. So I participate a bit in the Aerospace working group within ELISA, and there, of course, again, we are thinking about applications for a specific usage domain, in our case, the aerospace domain, and we have demo applications which we want to build. And so we need a build system. And we have multiple build systems at the moment, and one of these is based on Nix, and I came up with the catchy name of calling that Avionics. And so the second half of this presentation, we are going to talk about how we apply the technology principles that Erin introduced to solve this problem of ours, that we can package our demo applications for the Aerospace working group. I tried to make this as hands-on as possible, and the promise from the advertisement is that you should be able to run along the commands that we have here and should get the same results as I have. I think the slides will be published later on, so for now you can also maybe take my word for it, but feel free to run along. The first thing that we are going to do is that we actually check out the working group Aerospace repository. And then we'll go to a subdirectory within there, the demos/avionics demo subdirectory. And this is actually where I'm currently am. So you should be able to see a terminal now. And I'm exactly in that directory. We do want to check out a specific commit because we have a little bit of reenactment do later. So I'm going to check out this very commit here so that we get the very same result. Now, as Erin demonstrated or mentioned, there's usually a flake.nix file, and we have this here. There's an accompanying flake.log file that contains specific versions of repositories that go into this, in particular the version of the Nix packages repository, for example. And the first thing that I would always do when I see something with Nix is that I take a look at all the buildable outputs. Nix has a command for this, nix flake show, and this provides us with a list of different things that we can build. In particular, the most interesting thing here for us now is the packages, which are separated into different build system architectures. And for example, we see here on the x86-64 Linux platform, we do have a package which is called ELISA demo Python Lite. Now, to quickly jump back to the slides, we can start with a little aperitif. So we want to build this light application, and as Erin earlier explained, we are using the Nix CLI for this. So I'm just enter Nix build and then ELISA demo Python Lite. This runs really quickly, so we can time this, and we see that it took about 57 milliseconds. So the reason for this is I already have this package built. It's already in my Nix store, and Nix automatically checks that this very package was already built, so it does not need to be rebuilt. That's why it is so fast. We can, however, ask Nix to build it again. It takes a bit longer, but being a Python package, this mostly just means copying over source code, and so it's still rather quick. One side effect of running the Nix build command is that we have now a symlink that popped up in our current working directory, and this symlink points to the Nix store, and in the Nix store we have this package now. We can take a look on the insides of that package, and we see there's a bit of Nix support files, there's a bunch of Python files, they're also precompiled, and we have 2 binaries, or rather executables in the bin directory. And we can actually run these. So I'm going to run the Lite server here, then we have the Lite server. We don't really need to know what this is. This is part of an ongoing effort to build a demonstration application that simulates a light switch that is remote controlled. So a very, very simple demo application. All that we need to know is we can run this, and we are presented with a REPL where you can enter commands like changing a delay for light switching and increasing the delay, etc. pp. Okay, so this was the first thing. We just built a package, we compiled something, or not really compiled it, but put together everything we need for running it, and it seems to work. Let's jump back to the presentation and look at the next thing, which I deemed the pre-course. So the L in ELISA stands for Linux, and so really this means we want to use the Linux kernel, which means we need to have a Linux kernel. It usually comes in source code, and we need to compile it. That pretty much sounds like a package itself. And indeed, in the Nix packages, there is mechanisms to compile the Linux kernel with nice abstractions for various configuration tasks. The Linux kernel is a very configurable package. There's many things that you can turn off and turn on if you build a Linux kernel, and many things that you can change, like the architecture that you build it for. So let's jump back to the terminal, and let's build a Linux kernel. If we recall the Nix flake show output, then we know that there's a Linux kernel here which we can build, and this is directly available as a command. Again, this is cached. I ran all the commands before, so it's very quick for me, and it will not be very quick the first time you run this, because you first bootstrap the toolchain and the kernel before you can actually build the kernel. This leaves us again with a result symlink, which this time, if we take a look inside, contains on the one hand a system map. So this just maps memory addresses to functions for primitive debugging support, and a compressed kernel image. Sometimes it's interesting to look into the kernel, not in the compressed image form, but actually just as a program that is happily fed to debuggers. And for this, there's the sub output, the Linux kernel.dev, which will build us the kernel as ELF file. So if we take a look here, we have the result dev VM Linux, which is an ELF file containing the kernel with all the stuff. If we build the kernel with debug information, then this would also be an ELF file with the debug information, which is useful if you want to do kernel level debugging with QEMU and GDB, for example. There's various things that we can explore here. And if you take a look, there's many outputs, some of which are actually buildable within the kernel derivation. There's one more that I would want to take a look in, which is config file. If we take a look into the config file thing, then result is just going to be a symlink to a file directly. And this is the config file with all the final configuration decisions that were made for this kernel. You can see it's quite long, so about 2,700 lines. And this is everything that we turned on for building this Linux kernel. I think it is self-explanatory that when you're doing some kernel hacking, then this is actually quite useful. There's one last thing I would like to show. Previously, Erin also mentioned that we can get a development shell. And this is also true for the kernel. So we can, in particular, Nix develop, take this kernel and ask for the config environment. The config environment will provide us with a new subshell that has all the tools required to build this kernel for this target architecture in view. I'm going to just run the unpack phase of every Nix build here, which will unpack the Linux kernel source for us. Then I'll run the patch phase, which will apply Nix-specific patches to the software. For most, what we can see here, it rewrites the paths for shell script interpreter lines, so the shebangs, to a path that properly works in Nix. So it, for example, rewrites the hash mark, exclamation mark, bin bash to the absolute store path where we have the burn shell that is to be used in this build. Then we can run menu config, for example. So if I now make menu config, then I'll be presented with the menu config environment where I can configure the kernel. And where also I can explore different options for configuring this. So while Nix itself is set up to be this one command, everything happens alone in an isolated build environment, you can use the same declarativeness where everything you need as builder inputs and dependencies to also get an interactive development environment where you can do some interactive hacking. Sometimes it's much faster to iterate quickly in a dirty tree instead to always try to build the perfect package without any human intervention in between. Okay, so with that out of the way, I'm going to remove the remnants which we have here. So there should be the Linux directory here, Linux 6.18.2. Remove that, and we remove the two symlinks, and we are clean again. Let's jump back into the slides and combine what we have seen so far into something actually useful. So what we have here is, there we go. What we have here is our main course for today, which is building a fully integrated system using NixOS as a Linux distribution, Nix as a build system, the Nix packages as a big collection of Nix expressions. So we have four main components which go in here. We have the kernel itself, which we just built actually. We have a NixOS user space, which is already built and consists of the usual suspects of programs like the core utils with ls and rm, etc., pp, systemd as init manager, etc. Then we all built two applications that actually stem from the ELISA Aerospace working group. On the one hand, the light switch demo app, which we saw earlier, and NASA Copilot-based monitor software, which checks that the light switch application does the right thing. So to build this, we have a rather lengthy command here. It's not super convenient, but again, it is just a single command to get everything built and even running. I'm going to copy paste this command here in my shell. I'm actually going to substitute the run here for build because I want to take a brief moment to take a look at what comes from building this. Again, we find a results symlink, and in the results symlink, there's only one file. There's bin run ELISA demo CFS. And if you take a look at this, this is a very small shell script. And what it does is it runs qemo, and it has some configuration flags for qemo. It passes in a kernel, which happens to be the kernel we built earlier. It passes in an init rumfs that contains our entire system and enables networking. So if we run this, which would be the same as just entering nix run and then that very long flake URL path attribution thing, then this is going to start a QEMU. And in that QEMU, we have a user space, which is now booting through. And we should be able to log in. And now we have our system up and running. The interesting thing is, do our applications actually work? And so let's take a quick look at the ELISA demo CFS here. And it does not work. Actually, I started the wrong machine. That's too bad. So let's start another one. The name is different of the launcher here. That's the only thing I had to change. And see if this one works. And if we take a look at the relevant services which run our applications, then we see they are all active and running. So this looks good. However, it's not very satisfying to have a system that doesn't run. So we just
we have a question in chat if you want to answer that.
Oh, there's a question. Can you easily branch out from a given Nix package? Let's create a duplicate of the current package for the purpose of exploring further changes in a new package. Oh, absolutely. You can just copy the expression into your own tree and change it. And actually, we do have an example of this on the main branch, soon to be merged on the main branch in our repository. But Nix also considers every package just a function, and these functions are overridable. So a bit like class inheritance in object-oriented programming, you can take a package and say, I want to take this package, do everything as in this package, but in the patch phase, run this command, which, for example, changes some of the source code, inserts a patch with your changes. And it's very composable in this mechanism. That's actually what I quite like about Nix. I do have to do this every now and then. So, for example, some packages are not meant to be built for big endian PowerPC. And frankly, no one uses big endian PowerPC except people in Avionics. So I do have to care. And it's not uncommon that we have to do these overrides, and Nix makes this really easy. There's a bit of a learning curve on how to do that, but the mechanisms that you have at hand are quite powerful and work quite well. It's also no problem to have different variations of the same package. Yeah. So coming back to our problem here, we do have the issue that the command which I just ran built us a machine which didn't work as intended. So let's quickly revisit this. I now use just the Nix run command, which builds and then also immediately runs the main executable that stems from a package. So that's why I didn't have to have the second line with result.
We're still looking at your slideshow.
That's a good one. Thank you for the notice.
There you go.
Okay, so if we systemctl status, we can already see the system is degraded. And in particular, on this one, we have a NASA core flight system-based application. So that's a framework which lets you build applications for various things. Can Nix replace CMake? I'll go into that quickly. And what we can see here is this application does run for a moment. It prints some things, but then it actually exits with a non-zero exit code. So there's definitely a problem here. I think on the slides, we even have like the small joke here with the oops, so that's not good. Let me quickly get to the questions. So yes, Nix can replace CMake. However, that is not how I would use it in a project in which there is CMake. Basically, a build system is where somebody already put a lot of effort into compiling their software the way they think it is the right way to compile the software. CMake is one way to express this effort. And rather than replace it with Nix, I would just layer it with Nix. So Nix has CMake packaged and has excellent integration. Actually, the NASA CFS demo is built with CMake. And I don't know intricately how it is built, but also I don't need really to know. The only thing I need to know is that I put in the right dependencies, which are a bit complicated to get because the demo app also uses some Haskell-based programs for some pre-processing. And then I let Nix mostly just do the thing for me without me having to know so much about it. It's the second question I see. What is the benefit of Nix in this particular case in compared to just spin up a virtual machine and build the kernel in there? Then the image of the VM can be redistributed as well if needed. There's no guarantee that just building the image in there is actually reproducible. So increasingly more common, unfortunately, is that within the build system, if, for example, the build system finds out you're missing a library, it will do something that tries to fix this. So, for example, it will download the library and compile it ad hoc for you. Or I've even seen some code where a Python module tries to import another module in a try-catch block. And in the catch part of the try-catch block, it just runs pip install of that module. The problem with that is it's very easy to get a non-reproducible build from this, because if the pip install just, for example, happens to install the most recent version that is there, or if within the CMake file, it automatically just git checkouts the main branch from one of its dependencies and builds that, then you have an unreproducible build. If upstream changes, if there's updates, then you will get a different build result. And so that's the one end. The other end is you can do that. Actually, we have some people that use a virtual machine image which contains Nix to build the thing. So this is not exclusively Nix or virtual machine. You can definitely do both. And the last thing is versioning the images is hard, because in the end you have a big blob of binary and you don't really know what went into that. This is maybe a good point to retake the claim of declarativeness that Erin earlier brought up. When I do have a distro which I install, then I have a very complex stateful machine which is in some state. I don't really know what state it is in. Hopefully it's most of the time more or less the same state after installing it. Some things may differ, like usernames. And then I apply imperatively different commands to change, to mutate the state of this machine. And the hope is that I'm in one desired state at the end. With Nix, we eliminate the time, the state from this. What you get is what is the realization of the Nix expression you wrote. It doesn't matter what you had previously. It doesn't matter what the initial, there's no initial state. You just get from scratch the thing that you get from realizing Nix derivation. And so it eliminates state. With all of the stuff we have here in the Nix expressions, we have source code, which is rather concise, which defines what is the things we need, what is the dependencies we need, sometimes with comments that explain why something that is counterintuitive needs to be there. With a virtual machine image, you don't have that. You have something which hopefully works. You don't really know how you came there. It's not really documented. You can try to build the virtual machine image declaratively, which I think is a good idea, and which is actually what we are doing here. And Nix is one tool to do that. Next question. Oh, there's a lot of questions. Hope I'll not run out of time. How powerful is Nix as a build system compared to CMake or Bazel when starting a new project from scratch? I cannot really comment on Bazel. I lack knowledge in that area. There's a nice presentation or no paper on build systems that compares the two. I'll look up the link and post it to the YouTube video later. With regard to CMake, they have different scopes. So CMake tries to be a build system, and Nix is a meta build system. So I would use CMake to build the software, but I would use Nix to make sure, for example, all the dependencies, the libraries that I need to compile it are in view, which is actually what we do for the CFS application because it uses CMake as a build system. Okay, let's come back to our problem here.
Can I make a quick comment about Bazel? That's okay. So there's actually a really cool project called rules Nix packages, which includes Bazel rules to have your dependencies for Bazel managed from Nix packages and by Nix. So that includes or that ensures that all the dependencies that end up in your Bazel build are fully reproducible. And that's how you can combine the two. So you can call Nix from Bazel and you can call Bazel from Nix, and both are very powerful, but Nix cannot replace Bazel realistically.
Thank you for chiming in. So we have a problem which we need to troubleshoot, and this is a reenactment because this actually happened in an ELISA Aerospace working group call just a few weeks ago, where we tried to make the ELISA CFS demo on top of NixOS demo thing work, and we had this very problems. And I want to just replay what we did back then for troubleshooting because I think it illustrates rather vividly how Nix helps here. So as a quick recap of the situation, the kernel is running fine. So kernel is starting. The user space is running fine as well. So like systemd is coming up and we get like the getty in the end where we can log in. However, the NASA CFS demo app crashes with a non-zero return code just after a couple of seconds. Now our strategy to solve this problem is basically the same thing you would do most of the time. So step one is we want to get a debugger attached to the application to know where exactly the issue is. Step two is we want to actually find the issue. And step three is we want to fix the issue. And then if there's more issues, we want to fix them as well. So I'll go into these points in detail in the next slides. The first thing that we need to have is we need to get a debugger attached. And for that, we actually have subtasks. So we need to have the debugger there. That's easy enough. So I'll quickly jump to the terminal and we can go into the CFS Nix configuration thing. And there's this is like a NixOS configuration. So this is just a declaration of how a system should be. And in here, we are in the key environment.system packages. So this is globally installed packages which shall be available in our system that we built from this Nix expression. What we are going to insert here is GDB. So we have GDB. Jumping back to our slides, the next thing that we need to do is we need to get a binary with debug symbols. This brings me a bit into a pickle because I don't really know how CFS is built. I just packaged the Nix, but I'm not intricately familiar with the CMake scripts for that. However, luckily, Nix got us covered here as well. And what we can do is there's a function in Nix which is called enable debugging. And this is actually an override of a function, of a package function. So you pass a function that usually builds a package as argument to enable debugging, and it inserts specific environment variables for the compiler wrapper that inject the -g compiler flag wherever we need it, such that all the executables, all the binaries are compiled with debug information enabled. It also changes something in the fix-up phase so that debug information is not retrospectively stripped out again. So in essence, the only thing that we need to do is we need to provide this packages enable debugging as a prefix to all the places where you use the ELISA demo CFS package. You can see this in the patch on the right-hand side here. In the green, we have both in this ad hoc script, which is here, and then later for the definition of the service, this patch. And the last thing that we need to do for the debugging, we need to get the source code. Now you may say, hang on, we do have the source code, there's a tarball, but that is not necessarily the final source ball. Most of the time when distro packagers package software, they do have to apply some patches to make the software work on the given distro. And we've seen this with the Linux kernel. For example, we did a rewrite of all the script paths for the Nix store burn shell. It's also common that during the build you run a configure tool, which maybe even just generates header files, which obviously are missing before they were generated. So to get the exact source that then was fed to the actual compilation, Nix again as a function for us, packages source only, which we can apply to a package. And basically it runs the package build until when the actual compilation would set in, and then it just stops and copies all the sources over to the Nix store so that we have the sources with all the patches, but not the finally compiled result. Now this patch which we have here just cleverly combines both of this into a small shell script here, which essentially just launches GDB and sets the path for GDB so that it finds the source code. I'm going to apply a patch as it is listed down here in the slide to my code. I just did that here. And now if we take a look at the source code, then we can see the changes here. So the first thing is we inserted the GDB package. Second thing is that we have the small write shell application code, which just goes into one directory and then sets the substitute path for finding source files in GDB. And the last thing that we do is in the systemd service, which actually runs the ELISA demo CFS, we use the packages enable debugging override function to make debug symbols available in our compilation of the ELISA demo CFS application. This is all the changes we have. So if we take a look at git status or at git diff, then we can see this is it. With these changes in hand, I'll rebuild the virtual machine that contains everything from this demo application integration, and we try to find the problem. Once we are logged in, password is root, by the way, so we use our root password root. What we want to do is we want to run our little helper function, this script, debug CFS. This just starts GDB for us and sets the search path for the sources. Since we do have the sources available, what we can do now is we can enable the TUI mode, and we even get like a listing of the source code. First, let's verify that the problem is still present. So I'm running the application here, and what we can see is the application exited with exit code. So the problem is still present. It's quite useful for us to know that it exits with a non-zero return code, because likely that means it calls the exit function, and we can trap that. So we install a breakpoint on the exit function and run our program again. And we hit our breakpoint. We have no source code available because exit is defined probably in the glibc, which is not compiled with debug information. However, what we can do is we can take a look at the stack frame, and we see from where exit was called. If you move up in the stack frame, then we have actual source code. And here we can see the issue where our program decided to exit. Shortly after calling the shmem-get syscall to get shared memory, something is not good and the application exits. This gives us a big clue on what the problem actually is. I'm going to quit the virtual machine here, and we can take a look in the shmem-get man page. And basically, what we see here is that if we look a bit, that's a different man page than I looked up previously. But what we can find on other man pages online is that shmem-get actually comes from the systemv IPC model. So this is a syscall which stems from a different incarnation of Unix, where there's shared memory available as an inter-process communication primitive. And this means that we do need to enable the relevant syscalls in the Linux kernel. Let's quickly jump to the slides. Here's the steps for the debugging, which we just went through. And so we want to go and find the systemv shared memory and the Linux kernel, which is config guarded behind the config sysv IPC Linux kernel configuration flag. So we need to add this to the Linux kernel. And we can do that. Again, I have a patch for this one. Actually, this one is also checked in the repo. So what I'm doing is that I'll just check out to the next commit after the current commit we checked out in the very beginning. So we go here, we remove our current changes and check out that commit. And if we take a look in the diff with the stage changes, then we can see that we had to insert a kernel patch which enables two more kernel configuration options, the sysv IPC one and POSIX-MQ. POSIX-MQ, same story for finding it. If you go with debugging through, you find that at some point CFS tries to start a POSIX message queue, and the syscall fails, so it exits with 1. And then what we can do from this is that we change the configuration of the kernel to have these things available. Once we edit this, the rest of the changes here is just a different version of what we had earlier, so adding GDB, etc. We can quickly rerun the system, and this will recompile the Linux kernel. On my machine, it probably has done that. No, it hasn't. So we will recompile the Linux kernel quickly with this different version where we have the respective configuration parameters set on. And once the kernel is rebuilt, it will rerun QEMU. And hopefully we can see that our application is running properly then. In the meantime, while this is building, and due to time constraints, we move on the slides. There's one extra that is really nice in Nix, which is Nix properly abstracts over cross-compilation. So what this means is When we build a package in Nix, we think about 3 different platforms. So this should be on the one end, the build platform. The build platform is the machine on which we compile a package. So the build machine is the machine that currently is heating up my office for compiling another version of the Linux kernel. The host platform is the machine on which we want to run the program. In our case, we are not doing cross-compilation, so build platform and host platform are equal. But in other cases, this is not necessarily true. And we have demos in this repository where we compile, for example, from x86 to ARM v8, 64-bit AH64, to have that covered there. We also have one user in the Aerospace working group who uses an ARM-based laptop. So they actually do cross-compilation the other way around. They compile from ARM to x86 to have the same demos that we have. And as Nix properly, that's the target platform, last thing. In the special case that the package which we are building at the moment is itself a compiler, then the target platform is the platform for which this compiler can generate object code. Now, cross-compilation in Nix itself is super simple. The only thing that you need to do is you need to change the host platform that you want to build for to a different string identifying a platform and operating system, so hardware architecture and operating system. And Nix does everything for you. It bootstraps the toolchain, it bootstraps the compiler, it then compiles all the dependencies with this configuration and builds the final thing for you. Sometimes packages are not made to be cross-compiled, and you need to apply the override stuff and try to fix them. In the meantime, the build finished, so we can now run this fixed version of the ELISA demo CFS. And hopefully we can see that the application is properly running. And we see running, and this is the case. So if we look at the ELISA demo CFS, we can see CFS is still running and healthy. Good. I think that should conclude our talk. We have the takeaway points here on the last slide. I think Erin already gave a lot of arguments why Nix is interesting and potentially valuable. This is like my take in particular with the goggles for the Aerospace working group. So the first thing you should observe, most everything we do in this talk is a single command, which also means I can just tell someone, check out this repo, this commit, run this one command, assuming they have Nix itself. That's the only precondition. And probably they need a bit of RAM because compiling some of these programs requires a decent machine. And they will get the same result as I most of the time. The second thing is Nix scales vertically along the tech stack. So I can use this to build individual pieces, get my development environment, do Linux kernel configuration, actually with nicer abstractions than the upstream kernel provides, in my point of view. And you can build user space, you can build self-contained init RAM affairs. You can build virtual machines and use them for testing, and then you can use optical chair record recognition on the video stream from the machine to check whether your graphical program works. This is all integrated within the Nix packages repo using NixOS. So it's like everything. You can do mostly everything with that. The caveat is you get also the complexity of the solution, which can do everything. You have the proper caching mechanism. So you don't need to unnecessarily often rebuild things. And you can be quite sure that what you have in cache is fine. Also, what we do is we use a CI server, which builds all the things in CI and is configured as an upstream cache server for our development machines. So when somebody needs to get a version of the Linux kernel, which was already built by CI, their development machine just downloads it from the CI server because it was already built on CI. So you can save build time that way. And last but not least, we can abstract quite well over specific things in the build system. So I don't need to know how in particular to get a debug build. Probably there's documentation from the NASA CFS that tells me how to get debug symbols for CFS. I don't care. I just use the packages.enable debugging as an override to my CFS packaging solution, and I get a build with debug symbols. It's that easy. Thank you for listening. I think if there's any more questions, we can take them. Other than that, that's the last slide. There's
Thank
a
you,
good
Erin.
question.
Yeah, Thank you, Erin, and thank you, Wanja, for that very insightful talk on the technology. And we'll just stay here for a couple minutes and see if there are additional questions from the audience. Otherwise, thank you for participating in today's ELISA seminar. Appreciate your taking the time, and we'll see you at a future ELISA event. I'm going to turn off the recording.
There's one question from Pascal Vollmer. What is the relationship between DHAL lang and Nix language? And actually, I don't know DHAL lang, so I'm out for this one. Erin, can you comment?
I can definitely explain this. DAL lang is just a configuration language, similar to Nix. Nix the language, not Nix the ecosystem, not the Nix daemon, not the CLI, just the language. And honestly, they're just two different configuration languages. I don't think they were inspired much by each other, except that they're both vaguely based on JSON, but that's it. There are projects like GUIX that use Lisp instead of the Nix language to configure Nix systems. And then there's also Nickel, which was created by the Nix or by parts of the Nix team to hopefully eventually replace Nix as a language, because it's not the nicest language. And possibly you could implement a tool that creates derivation files from DAL, but I'm not aware of such a thing existing. You're welcome.
Great. Yeah. Thank you again, and appreciate the time. And we'll see you participating in the ELISA working group and at a future event, either in person or virtually. Thanks again. Bye.